So in order to do this problem, I've given you a whole picture that has the circle involved and a bunch of other things like that. But really the circle isn't changing how we approach it. This problem really is going back to this kind of a basic setup like what we were first working with yesterday when we reviewed our right triangle trigonometry stuff from geometry. Now in this case, I know that angle O is 72 degrees and I want to find angle X. I'm sorry, side X. What do we call side X? Is it the opposite, adjacent, or hypotenuse?
Adjacent.
It is the adjacent, yeah. So X is the adjacent. And notice in the diagram we're also told about the side that is 1 unit long here. What do we call that side? Yes, that is the hypotenuse. So which of our trig ratios involves the adjacent and the hypotenuse? And if you're feeling a little rusty, what's that word we can remember? Remember SOHCAHTOA. And so if I'm looking for the one that involves adjacent and hypotenuse, that's right there with the A and the H. It's attached to the C, so it's got to be cosine. So we've got cosine of the angle, because it's always of the angle, equals the adjacent x over the hypotenuse 1. Now this particular problem is very specifically chosen, as you'll continue to see as we go on today. Because notice here we have x over 1. Now, I could go ahead and multiply both sides by 1. Or, what does x over 1 equal? Just equals x. And so whether you see it as multiplying both sides by 1, or I think the simpler, x divided by 1 equals x, we can see here that in order to find x, I'm going to be doing cosine of 72 degrees. I'm not having to multiply it by anything this time. I'm not having to divide anything this time. It's just cosine of 72. So, do that calculation. Make sure that you can get this number out. You should be finding that x is about 0.31. Now I say still do the calculation, because what if you're getting the wrong number out? It tells you need to check something on your calculator, right? If you don't get the right number out for this, what should you check?
Degrees.
Degrees, yeah. You should be in degree mode for this problem. And so, notice again, if I put that circle back in, it's still the same problem. Today we're going to be doing a lot of that work with the circles. Just to continue practicing this idea though, let's go ahead and find y to round this out. So please now find y using the same kind of technique you used to find x. So now to find y, I again think about what do I call the different side lengths involved. So what do I call the y side? And remember I'm going from that central angle there. The y, yes, is the opposite. And what do we call the one side? It's still the hypotenuse, yep. And so which of our trig ratios involves opposite and hypotenuse? So it's got to be sine of 72 equals the opposite y over the hypotenuse 1. And again, just like the last one though, y over 1, that just equals y. So y is going to be sine of 72 degrees. So why did I start with this one side being 1? Because you already noticed one of the cool things about that is that if that hypotenuse length is 1, there's no multiplying by the sine, there's no dividing the sine, it's just what's the sine of 72. And so if I actually do that calculation, then I find that y is about 0.95. Now we're going to be coming back to these ideas here in a little bit as we go forward. So keep this drawing and keep these examples handy, because we're going to again be coming back and talking about x and y. I'd like you now to please add this new definition into our notes, because it's going to be all that circle stuff that we're going to be basing all the rest of our work on. The unit circle to be precise. Alright, and so notice what this is telling us. It's telling us that a unit circle is any circle that is centered at 0, 0. So that tells me at this point here in the middle of our circle is the actual coordinate pair 0, 0. And that it has a radius of 1. And remember, the radius is the distance from the center out to the edge of the circle. So any of these segments that go from the center to the outside are 1 unit long. That's actually why it's called a unit circle. It's called a unit circle because the radius is 1 unit long. Now, a few little details which are probably fairly familiar, but it's good to make sure that we are all on the same page. When we're measuring any angles inside our unit circle, we always go from the right horizontal. So I'm always going from this little part of it over here. And then we're going counterclockwise from there. Now, up to this point, all the triangles we've built have been nice, pretty right triangles that have really lived up here in the first quadrant. But what you're going to find is that because this is a circle, we can go all the way around, and we can end up with some really interesting looking angles, and we're still going to be able to use the same properties we see with those with this. All right. So continue to build on that diagram. Notice I can take my picture of my unit circle and drop a segment straight down from this point where our line hits the circle and make that into a right triangle here. Go ahead and draw that addition into your circle picture in your notes. Now, in our warm-up, I chose the names X and Y very specifically. You'll notice from our warm-up problem, X was how far we were going over, and Y was how far we were going up. Isn't that how we get coordinates of a point? We start at 0, 0, and then we just see how far over do we go to find X, and how far up do we go to find Y. Remember how we found those values in that warm-up? X, we did cosine, and to find Y, we did sine. And the same can be true of any point on the circle. And so the actual coordinates of that point, X and Y, can be found by doing cosine of the angle, comma sine of the angle. So add this to your notes as well. And then with this information in mind, going from here, if you ever want to find the X or Y coordinates of any point on the circle, you're just going to use this rule here. Cosine for the X, sine for the Y, every time. And so, of course, I'm going to want to practice this idea. So, next up, I'd like you to please write down this problem. Here we have a unit circle. The angle is 108 degrees. Find X and Y. Now, you'll notice that it might seem like it's kind of vague, but it's actually given us plenty of information to know exactly what we're looking for. It says the measure of the angle is 108 degrees. It doesn't specify which angle, but we should always know going forward, because remember that the angle is measured from the right horizontal, and it always goes counterclockwise from there. So this is the angle that we're talking about here. So this is the one that's 108 degrees. And then when it says to find X and Y, what we're saying then is we're finding the X and Y coordinates of that point. The point where that angle, the radius of that angle, hits the circle. So this is really what it's saying. Find that X and that Y. Now from your notes, you hopefully can see exactly how we do that, because you just wrote down into your notes, how do we find the coordinates of any point on the unit circle? Now a reminder, how do we know what it is? If I visualize a right triangle being drawn there, Y is how far I'm going up, X is how far I'm going over. Remember we found earlier that we could use sine and cosine to get those. Sine for the Y, cosine for the X. And so that's what I'm going to do to actually find these values. So, to find X, am I going to use sine or cosine? Cosine. So we do cosine of 108 degrees. And notice there's no multiplication, no division, because it's a unit circle. The fact that that's that unit circle makes a lot of these things so much easier and so much smoother. Do that calculation, you should find that we get about negative 0.31. Now, why is it negative? Well, if we think about that right triangle that this is really creating here, in order to be able to get to our point, I'm right now finding this X coordinate by going to the left. But if we go to the left of the origin here at 0, 0, I'm going into the negatives. And so by using that original angle of 108, it also tells us if it's positive or negative for that coordinate. Next up, to find the y. Would you expect the y to be positive or negative here? Well, are we going up or down? We're going up, right? And since we're going up, it's got to be positive. And again, to find y, that's the sine. So the sine of 108 degrees, that gives us about 0.95. All right, so that then tells us the coordinates of that point are negative 0.31 and 0.95. You can use the same process no matter what the angle is, and you're going to be able to figure out what the coordinates of any point in the circle is. So next up, we're going to be taking a look back to some stuff we did yesterday. Yesterday, we looked at 45, 45, 90 triangles. Today, we're going to be looking at the 30, 60, 90 triangles and seeing what those exact side lengths are, because they're going to let us know what some exact values are of sine and cosine as well. All right, so I'm going to lead you through the process about how we can find this. It doesn't mean you have to be able to go and do this exact same process every time. In fact, you don't have to do it every time. You only need to do it the once to figure it out. But I just want you aware of where these numbers are going to be coming from. So the strategy with the 30, 60, 90 is that we can actually build the second half of that triangle flipped onto the right side. It's the same triangle, which means that this angle in the bottom right is also 60 degrees. This angle in the top is also 30 degrees, because it's still a right triangle. Now, that angle up at the top there, the 30 and the 30, how big is that total angle? 60 degrees. Knowing that, what kind of triangle is this? It's an equilateral triangle. Because since all the angles are the same, that means the sides also have to all be the same length. That's what's going to let us then start figuring out the side lengths of the one half of the triangle. Because if that whole bottom triangle side is 1, how long is that part? It's got to be half of it, right? Yeah. So that side length really is 1/2. Now once we know that, I now know two sides of my right triangle. I can find the third side. I'll go ahead and just call it x just for the time being, just as a placeholder. I can find x using the Pythagorean theorem. So how would that look? I would do 1/2 squared plus x squared equals the hypotenuse squared. So that equals 1 squared. And then we could actually do that work. Now, when doing 1/2 squared, you square the top and you square the bottom. So 1 squared is 1, 2 squared is 4. And then 1 squared, of course, is 1. And so if I want x squared by itself, I subtract 1/4 from both sides. 1 minus 1/4 is 3/4. Then one last step to figure out what x is, I have to get rid of the squared, which means taking the square root of 3/4. And just like squaring a fraction, you square top and bottom, to square root a fraction, you square root the top and square root the bottom. So the square root of 3 on top, well, that's just square root of 3. Square root of 4 on bottom, that's actually 2. So then that other side length then is root 3 over 2. And that's how we can know those. Now to break it out, this is the actual picture cleaned up of what those side lengths are. And then we can use that picture to figure out the exact values for sine of 60 degrees and cosine of 60 degrees. So sine of 60. First of all, sine, remember our definition, opposite over hypotenuse, right? What's the opposite of the 60 degree angle? That's got to be over here, right? So my opposite side length is root 3 over 2. And if it's going to be opposite over hypotenuse, my hypotenuse here is 1. But I don't really like the look of root 3 over 2 over 1, because anything over 1 is just itself. So the exact value of sine 60 degrees is root 3 over 2. Now if you type in sine 60 on your calculator, it's going to give you a decimal. That's an approximate value. Root 3 over 2, this is the exact value. What makes it exact is because I can actually write it precisely, whereas your calculator answer, it is a rounded decimal, because the square root of 3 is an irrational number. It's a decimal that goes on forever and never repeats itself, just like pi. And so just like pi, the only way we can write it exactly is symbolically. All right, cosine of 60 degrees now. Cosine is adjacent over hypotenuse, so that means it's got to be 1/2 over 1, which is, of course, just a half. So cosine of 60 is a half. Now we can use the same reasoning to find sine and cosine of 30 degrees. I'm just turning my triangle over so that it looks the same way as it does when we see it in the unit circle. So sine of 30 degrees. What is the sine of 30 degrees going to be? Opposite over hypotenuse, right? So 1/2 over 1 is a half. Now if the sine of 30 is a half, what's the cosine of 30? Yep, it's got to be root 3 over 2. If one of them is a half, the other one will always be root 3 over 2. Or conversely, if one of them is root 3 over 2, the other one will be a half. You're going to notice that's an important pattern to know going forward, because it's going to come up as we look at the bigger circle as a whole. The only thing that we would have to be aware of in that statement is that the signs might change, like it might be a negative 1/2 instead of a positive 1/2. So these are the two special right triangles. Now, if you don't already have these two copied into your notes as pictures, I would suggest that you put them in there right now, because they explain why some of these sine and cosine values are what they are, and plus, they just look cool. And then next up, I want to practice using these exact values that we just found. So I'd like you to go ahead and write down this problem, then we're going to work it through together, but we're going to do it entirely without relying on our calculators. So the first thing I do when solving this problem is I draw it and label the picture with just the parts that I need on it. So you'll notice that's what this looks like here, where I have my 60-degree angle, the 14, and I've marked that I'm looking for the value of b. So as I take a look up at that, I now need to know what do we call each of those sides. So the 14 side, what do we call that side? That is the adjacent. And what do we call the b side that I'm going to try to find? It is the hypotenuse. And so, which of the trig ratios involves the adjacent and the hypotenuse? That would be cosine. So, we're going to do cosine of the angle, so we're going to do cosine of 60 degrees. And that equals the adjacent over the hypotenuse. The adjacent here was 14, and the hypotenuse here was b. And then we go through and we proceed like we always would have. And again, remember, we can do this without calculator. So I start by multiplying both sides by the b. So that gives me b times cosine of 60 degrees. Equals 14. And then this is one of those where I happen to have one more step from there, where I have to now divide both sides by the cosine of 60. So b equals 14 divided by cosine of 60 degrees. Now up until this point, this is where we break out our calculator. And yet I said we could do this one without the calculator. That's because we actually know what the exact value of cosine of 60 degrees is. The cosine of 60 degrees was 1/2. And so really what we're doing is we're doing 14 divided by a half. Now remember how we divide by a fraction. That means I'm going to do 14 times the reciprocal, so that's going to be times 2 over 1. So that's 14 times 2, so b equals 28. No calculator needed. And as we move forward, I'm going to expect you to give me exact values like this and not even rely on your calculator. Anytime the angle that we're putting in there is 30, 60, or 45. So I want to do one more of those. Please write down this problem, and then we will again take a look at how we could do this one again without a calculator. So step one is to draw and label our picture, so that's what we're looking at now. So I know where my 60-degree angle is. I have the 10, and I'm looking for C. Let's identify what we call those sides. So this side that's 10 units long, what do we call that side? Hypotenuse, absolutely. And what do we call the C side?
Opposite.
It is the opposite. And so which one involves the hypotenuse and the opposite?
Sine.
So it's got to be sine of 60 degrees. And it equals opposite over hypotenuse, so my opposite is C, my hypotenuse is 10, so C over 10. Now we solve like we always would have before. So in order to get C by itself, I'm going to multiply both sides by 10, which gives me 10 times sine of 60 degrees. And then I have to figure out what sine of 60 degrees is. Without a calculator, I said. That's because that's one of those values we actually can know. Now, we just saw in the last problem that cosine of 60 was a half. What does sine of 60 need to be then? Yep, it is root 3 over 2. Now, I don't want to leave my answer looking at like 10 times the square root of 3 over 2. So I'm going to go ahead and clean that up. In order to multiply by a fraction, I turn the 10 into a fraction. So 10 over 1 times root 3 over 2. Then we multiply straight across the top. Which gives me 10 root 3. Multiply straight across the bottom. That gives me 2. Can that fraction reduce?
Yeah.
Yes, it can. Notice the 10 and the 2, I can divide both of them by 2. So C just ends up equaling 5 root 3. And notice then we've also been able to give our answer as an exact value. We aren't having to rely on our calculator to give us some rounded answer. This is actually the exact value. Then the last thing I'd have you do is add this into your notes. This kind of summarizes those exact sine and cosine values that we've been looking at. One little note about this, because I don't think I've brought it up before. Notice that little symbol inside the parentheses there. It looks like a 0 with a line through it. If I draw it bigger, it kind of looks like that. This is called theta. It's just a Greek letter, and it works like any other letter. It's just very commonly used to represent angles.